right, we'll edit later. All right, so we're going to look at local linearization and tangent line approximations today. So the idea is simple. We have a function f going through the ordered pair x naught, y naught, where y naught equals f of x naught. That's one point on the actual function. And the goal or the idea is that we know what happens to the function at that point. We want to use that information to try to get information about what happens near that point. So here we have the curve kind of zoomed in. And our basic tools use the tangent line. So I'll draw that in here. We get the following picture there. And the idea is straightforward, that near the point x naught, y naught, the tangent line and the curve are very, very similar. I'm going to draw this fairly large to kind of make a point. But I'm going to draw in a couple of triangles. And then label some things here in the picture. Let me move my x naught, y naught over here. This distance I'm going to call delta x. That's the change in the x in the function, from our known value of x naught to some new value. This is the new point on the curve, xy. So again, what I've done here is I've said that delta x equals x minus x naught. And equivalently, we're going to define delta y to be y minus y naught. This is already way too small for the video. You all laugh at that later. So this distance here is delta y. Now, what we're going to understand is that this distance here is very hard to get your graphs on. However, this distance actually is a lot easier to grasp, because I can call this dx. Being the slope of that line is the derivative, I can call this distance dy. The approximation we've used in class quite often is that delta y over delta x is approximately what we know is dy over dx. Or equivalently here, that delta y equals dy over dx times delta x. Or taking these two things and put it in this, y minus y naught equals dy dx over x minus x naught. If you think back, this should look awfully familiar to you. This should look a lot like the point slope formula. We had an m here before. Since it's a lot of change, we're going to call this now the derivative. Now, I guess I fudged this thought. These all should be approximately equal to. And this is typically written is that you get a new function y, which I'm going to call L of x, to be y naught plus f prime of x naught times x minus x naught, where this is dy dx at x naught. And this is our formula for the tangent line approximation. Again, this looks very familiar to that one over there. I just moved the y naught over and written in terms of f prime instead of the dy dx.
After the f prime, what's the first x?
X naught here, x naught there. In this equation, there is an x input on the L. The only place you're going to plug in an x is right there. Everything else is given off the point. Okay? So let me ask you from this 2 questions which lead into one another. Again, this is either called the local linearization or the tangent line approximation to f near the point x naught, y naught, or simply near x naught, depending on who's saying it. So find the tangent line approximation of f of x equals the square root of x near x equals 4. So 4 is a very nice point for the square root function. And the key idea is that we want to use the x naught, y naught is a good point. X naught, y naught, or equivalently x naught comma f of x naught, in this example is 4 comma square root of 4, or 4 comma 2. And if f of x equals the square root of x, which is x to the 1/2, this implies that f prime of x is 1 over the 2 square roots of x, like we've seen before, which implies that the derivative at the point 4, because we're trying to understand not the derivative at all values, but only at the nice point, should be 1 over 2 square roots of 4, or 1 over 2 times 2, or simply 1/4. So leaving our formula there, when I write this down, I get L of x equals y naught, which we agreed was 2, plus the slope, which is this calculation, 1/4 times x minus x naught. If you've done this correctly, there should only be one x in the equation. A very common mistake is to write the derivative formula down here. Usually it's not even a straight line. But this is a straight line. Now, this is the way to write it down based on the formula. You can either leave it like this or clean it up. In most cases, it's actually not all that beneficial to clean it up. I'll mention in this case, if you were to, it would be 1/4 x plus 1. You want to put it in mx plus b format. And we'll compare the 2 uses of this in just a second. So a second question. Approximate the square root of 4.03 without the aid of a calculator. Well, if we use the previous problem here, if f of x equals the square root of x, then the square root of 4.03 equals f of 4.03. Now, what we know is that f of 4 equals what I've called L of 4. I've attached the line to the function at the value 4. The linear approximation, or local linearization. And thus that f of x is similar to L of x if x is near 4. If it actually equals 4, they're equal. if x is near 4, f of x is almost L of x. And details here, the closer x is to 4, the better off this should be. So again, this value, 4.03, is pretty close to 4. So this should be a decent approximation. So L of 4.03 should equal 2 plus 1/4, 4.03, that's horrible, minus 4, which is 2 plus 1/4 times 0.03. That's the delta x we had before. That's how much you've moved from the known x to this new x. It's just the calculation we've been making for quite a while now. Well, this can be done with just a little bit of scribble work. You get 2.0075. Something you all could do with pencil and paper if you had to. Again, 3/4 is 75 cents. Just make sure you keep the right number of decimal places. 2 decimal places, 4 decimal places, 1, 2, 3, 4. So we can approximate the square root of 4.03 as 2.0075. Square root of 4.03 via technology is what? Someone has a calculator out, don't they? Good. So this approximation was actually really, really good. With what we've seen here, this is a way to get information of unknown values. Again, how could you figure this out without a calculator? Well, it's not that easy. But you knew the value at 4. Therefore, you can make an approximation based off the information you know at 4. So again, you can see these two things are very similar. And this would be then approximately f of 4.03. Notice that f and L are very close. Questions? Yeah.
So this is just kind of more general topic than this specific formula and stuff helps us to figure out the equation of the line that's close to the tangent.
What this does is pretty straightforward. That's the 0.42. That's the curve f of x. What we've just done is found the equation of the tangent line, which attaches to the curve at that point. This line is what I've called L of x. So if you were to plot both f of x equals the square root of x and L of x, which equals one of those two forms, you're going to get these two things are indeed tangent. And the idea is for values near 4, the line is very close to the curve.
Why isn't it exactly?
Because the line is not, because the curve is not straight. Again, the two things do match at 4. But if I zoom in hyper quick or really far in, I'm going to see is a curve, and not drawn to scale, the curve which is just really close to it. Since this always has some curve to it, the straight line can't perfectly stay on the curve. Because one's straight and one's curved.
Where do you get the 1/4 from?
1/4, this was f prime of 4, which is 1 over 2 square roots of 4 from the formula. And this is the m in point slope. Some people memorize this formula based off point slope formula, which is totally fine. Okay, the formula that I've given you is that L of x equals y naught plus f prime of x naught times x minus x naught. Can be thought of simply y minus y naught equals m times x minus x naught, with m equaling the known derivative. But again, the biggest mistake people make is leaving this in terms of a function and not a number. This needs to be a slope and not a derivative function. If that makes sense. Let's do one more example. See if that kind of assuages some fears. Let's find a tangent line approximation of f of x equals, let's do the natural log of x near x equals 1. So a quick sketch of said function. Looking at that point. Call it x equals 1 is the x-intercept of this function. So x naught y naught, or x naught f of x naught, in this case is 1 natural log of 1, or 1, 0, which is the ordered pair right here. What is f prime of x? First do it in terms of a function. What's the derivative function of log x? What's that? Bingo. But don't leave it like this. You have to write it in terms of the known point. What is f prime at the x value we're interested in? 1. Well, that's 1 over 1, or simply 1. This is thought of as your slope. This is the m of a tangent line. This thing's dead. I just need to plug it into the machine. It's rechargeable.